Okay, I hope you're slowly getting back into the interiors of room number 1. Just once again, I want to say that I'm really happy to have you right here in Wrocław, in the place where Code Dive has been since I can remember. So this is the 12th edition of this conference. We are online via room 1, 8, and 9 with different hosts, with different set of guests, and with different lectures and different topics as well. But C++ is definitely the main topic for today. But in the background, we're just giving you some nice entertainment actions, which I would like to mention before we start our next go. So please remember about the Wheel of Fortune. So this is the place where you can get something on top of the packs that you already, I hope, you were given. If not yet, please remember to collect them. Remember about the photo walls and about actually getting your photo with the proper hashtag just to be a part of the Code Dive community 2025. And please also remember that you can also enter another world with our VR space. So Virting VR Arena on the first floor, just one of the attractions, but definitely not the last one. So we spent some time with John, but as we say, we never stop. We just continue until 7 p.m. We have plenty of time to make use of this fact. And actually, like to remind you that we would like to pass some knowledge about Wrocław as well to you. So I am just going to, hopefully it will work for me, to give you some, will it work? It's off, now it's on, okay. So, some facts about Wrocław. Named after a Czech duke, Wrocław was named at least in a couple of ways. So first of all, after Władysław, a Czech duke from the 10th century. The name evolved over centuries, of course. Then we had Wrocław in Old Czech language. Then Wratysławia given in Latin. Then there were plenty of centuries spent right here in Wrocław where people were not talking about Wrocław but about Breslau. And then there was a total mishmash after the Second World War, and suddenly Wrocław appeared once again, or maybe for the first time in its proper sounding way for us, of course, the Poles. So Wrocław is actually the name that probably most of the English-speaking communities try to use, but whenever they come to our radio, I am also part of Radio RAM, so they say, Maciej, but please tell us, how do you pronounce this city? It's Wrocław. So in Wrocław, we have another guest who I would like to present right now. So Timur Doumler is a co-host of CPP Cast and co-chairs SG21 contracts in the ISO C++ committee. With a PhD in astrophysics, please remember, he changed from simulating galaxies to building audio tech, co-founding Cradle, and working at JetBrains on C++ tools. On top of that, we have to say that he's based in Finland. He organizes the C++ Helsinki meetup. He's also passionate about clean code, low latency, great tools, and pushing C++ forward. But now comes the best part, and I would like to show it to you because we promised to ourselves that there would be fun facts. So have a good look at the picture. This is Timur playing guitar and bass, and he likes progressive metal with complex rhythms. If you like metal as well, not only can you talk about C++, but also about music right after his presentation. Ladies and gentlemen, I would like to say that I think you're the best audience wherever you are, whether you are seated inside this room or outside somewhere there via the net. Please take your hands together and please give a warm welcome. Firing up the mainframe of knowledge. Give it up for Timur Doumler, please. Thank you.
All right. Hello. Thank you very much for the introduction. I did manage until today to keep my C++ persona and my heavy metal persona independent from each other, but it seems that now, yes, you have seen this. So yes, this is another alter ego that I have. But today I'm not going to talk about metal. I'm going to talk about C++. Thank you very much for inviting me here. I have actually been to Wrocław last year. We had a committee meeting here. Very, very nice city. But so I'm here for the second time, but I'm for the first time at this conference. So somehow I managed to avoid it until now, but I'm very, very happy that I finally made it here. It's a very beautiful venue, beautiful conference, great audience. Thank you very much for coming. I want to talk about safety and security and correctness in C++. And that, as we have heard, is quite a big topic right now. And I want to try and take a holistic approach. And so that means we need to start at the very top. What is a good program? A good program has a bunch of properties, and there's some properties that I'm sure you can name. Can you shout out some good things that a program should be? All right, it should work. Yes, of course. But like if you read any programming books, you will see that there's all of these things that people always write about and talk about. It should be maintainable, extensible, portable, etc., etc., etc. There's also a property that C++ is particularly well known for, which is efficiency. There's also, of course, cost effectiveness. A program is no good if you can't afford to write it and release it. And then there are these two properties, safe and secure, which are very good and important properties. As we have heard, people are paying close attention to that now. And we're going to talk about those. But there's actually one really important property at the very top missing. Can somebody tell me which one that is? What's missing? Correct. Thank you, Andrzej. Correctness, of course. And so, yes, we're going to talk about those. But first, we're going to talk about correctness. And correctness is really important. I actually managed last month to read this book by Bertrand Meyer from the 90s, who is the person who invented contract-based programming, and a lot of our work that we have done for C++ 26 on contracts is based on that. And one thing Bertrand Meyer says in his book is that correctness is the prime quality. If a system doesn't do what it's supposed to do, everything else about it, whether it's fast, has a nice user interface, etc., 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 matters little. And I think this is really, really important. Correctness is really the thing that makes a program, worth, developing, running, selling, using, etc. It is really the prime quality. It's the thing that we need to ensure above everything else. So we need to figure out what we mean by that and how we can make our program more correct. And it turns out that's actually really, really, really tricky. Because like with many of these terms, different people have different definitions of correctness. One thing that we saw just in this quote by Bertrand Meyer is that correctness is not an absolute property, actually. It's always relative to a specification. And the other thing that, if you're a mathematician or a theoretical computer scientist, you might disagree with me here, but I'm going to just put this on the slide anyway. Correctness in general is not something you can prove. Yes, you can disagree with me on that. And you can point out that, in mathematics and in computer science, there are ways to approach correctness kind of from a theoretical perspective. There is this concept of a functional correctness, where a program or part of a program is functionally correct if for any input, the output satisfies the specification. Now, you can divide this further up and say it's totally correct if for any input it actually produces output, and then that output matches the specification. And of course, if you want to prove that, it turns out this is an undecidable problem in general. You run into the halting problem. So then you can say, OK, a program or a part of a program is partially correct if it does produce output, like we know that somehow from somewhere else. But then if it does produce that output, then that output satisfies the specification. And then you can do some formalism around that. There is the whole logic and all kinds of different approaches built on top of that, where you can kind of have a formalism around reasoning about correctness in that way. However, if you want to apply that to real-world code bases, it typically doesn't scale. It typically is not something you can use in practice unless the problem is kind of very small and self-contained, because the real world is really, really messy. What even is the specification? Where and how is it specified? What is actually the input and the output? Obviously, we have parameters, we have the return value. What about C in, C out. What about data being sent or received to the network? Is that input or output? What about side effects? You're manipulating some state somewhere else in the program if you call a function. What about other requirements that have nothing to do with the input or the output? For example, this function needs to return within a millisecond, and if it doesn't do that, it's a bug because you're in a real-time system, right? And what about not doing certain things, right? So what if we say that our program is only correct if it doesn't touch this memory or it doesn't do something else? We're going to talk about nasal demons later in the talk. And so we arrive at a kind of practical definition of program correctness, which is that we can say that a function or a class or some other component of a program, which we call an entity, has a contract. And that contract is the set of expectations that we have on the behavior of that entity, right? So we have some expectations when we consider that function or class or whatever to be correct, and the contract describes that, right? And so some of these are going to be explicit, some are going to be implicit. We're going to talk about that as well. And this contract consists of multiple contract conditions. Functions have preconditions and postconditions. So preconditions are the expectations we have on the caller of the function. For example, what parameters it's going to put in or what state the program needs to be in at the time you call a function in order for that function to be considered correct or that call to be considered correct. And then postconditions are talking about what the function ensures, right? It runs, it returns a value, it leaves behind the program in a certain state. And we have some expectations on that state. And if those are fulfilled, then the function did what it was supposed to do. It fulfilled its postconditions, so it's correct. Okay? And so for classes, we have invariance. For loops, we have variance and invariance. And yeah, a correct entity is one that satisfies its contract. And then we can say that the essential behavior of an entity is the behavior required to satisfy its contract. For example, if you talk about vector pushback, when is an implementation of vector pushback correct? Well, it's correct, if it takes the item, inserts it at the back of the vector, and then there is non-essential behavior. For example, you can ask if pushback does what it's supposed to do, and then it also prints hello to cout. Is that still correct? That depends. If the contract says and it should not print anything to cout, then it's not. Maybe it's irrelevant because nobody cares whether it prints anything to cout. And then it's not part of the essential behavior, but it's also not incorrect. The important thing is that only the human knows what is correct. So, but if then the program violates the contract, then we have a contract violation. So that happens when a program fails to satisfy our expectation. And the really important thing to remember here is that a contract violation is always a bug in the code, and that makes it different from an error. If you receive bad input or something goes wrong, the network is not accessible anymore, kind of outside of the program, then that's an error, and you need to deal with that via error handling. Whereas a contract violation, you can only really deal with by fixing the bug in the code. So contract violation is something else from a runtime error. It might lead to runtime errors, but it's usually a bug in your code. So we need to specify this contract, right? It turns out that there's different ways this is done. Often the contract is specified implicitly. It could be coding conventions or common sense, things like, if you have a const member function, you expect that to be thread safe. That's a common convention, for example. You don't write that down on every function, right? That's just something that, implicitly, you just assume that's part of the contract of every function you write if you work in a place where the code base has that convention. And then there is explicit contracts that you specify in human language. Very often you do that in a comment above the function's declaration, right? It's kind of like, this function does this, and if you do this, this is wrong. Or maybe in a separate document, like we do in the C++ standard. In the C++ standard, the preconditions and postconditions of every function in the standard library are specified in English there. And interestingly, you can also specify the contract in code via assertions. And so today, you can do this with cassert and a bunch of other assertion macros. And since in C++ 26, you will be able to do this with a much more powerful feature that we have been working on for a while, where you can write preconditions and postconditions with pre and post, which go in the declaration, and contract assert, which goes in the body. And so all of this together is, we call this the plain language contract. So that's the whole contract of a function or of a class. And then contract assertions typically can only encode a subset of that, right? So there's parts of the contract that you will not always be able to express in code. So this talk is actually not about contract assertions, so I'm just going to briefly cover them, but there's other talks out there on YouTube that you can watch that go into a lot more detail. I think the first one you should watch really is Lisa Lippencott's talk from last year's CPPCon, which really explains the whole idea behind the feature. Then Herb Sutter had a great talk just last month at CPPCon this year, which I think is a fantastic intro. And then I also did a talk earlier this year at ACCU, which goes a little bit into the guts of like how the feature works, what to do, what not to do. And then obviously today we had John Lakos who covered some of this. We're going to have a talk just after this one by Andrzej Krzemienski, who I believe is going to talk a little bit more about the feature. So please stay for that. That's going to be great. I'm just going to literally do like a 2-minute overview so that you have kind of the context. So in C++26, you will be able to express the precondition of a function, for example, here that the index needs to be smaller than size with this precondition assertion here on the declaration. It doesn't have to be about the parameters. It can also be about just the general state of the program or the object here, for example, front has a precondition that the vector is not empty. If you call it on an empty vector, it's UB, right? Clear has a post condition that afterwards the vector is empty, so you can also write post conditions now in C++26 directly like this, and those post conditions can also refer to the return value of a function directly, so you can put an identifier there and then say colon, and then that identifier is going to refer directly to the object that is returned from the function, which is not something you can do in C++ today, so that's interesting. And so each of those assertions can be evaluated with one of 4 semantics: either ignore, which is do nothing, the code just goes away; observe, check the assertion. If it's false, if you have a contract violation, you call the contract violation handler, then you continue. Enforce, call the contract violation and then terminate, and then quick enforce, just terminate immediately. And all of those have different use cases, different trade-offs. They're useful in different situations. You can choose which one you want to use. The compiler is going to give you flags for that. This is a whole big topic. I'm not going to talk about that very much here. You have this contract violation handler that is going to get called, and then you have this little contract violation parameter here, which is going to tell you where the error occurred, what line, source, you get a source location, etc., etc., etc. So the important thing for this talk is that this is very useful, but you cannot actually express the entire contract this way. Sometimes you could, but it's kind of very verbose, and sometimes we don't have the features yet to do that. We might get some of those in C++29, so C++26 is kind of just the initial feature set. And some other things you just cannot really express in code. For example, operator square bracket also has this post condition that, the contents of the vector are the same as before, right? Things like that. You don't want to necessarily express this in code. There is also here pushback. Pushback has obviously a post condition that now the last item is the one you inserted, or it compares equal to that. But you also have a post condition that if it succeeded, if it returned normally and didn't throw an exception or something, then the size of the vector is now 1 more than it used to be. And this is not something we can write in C++26. We need a feature called post condition captures for that, which we're hopefully going to get in C++29, which looks like this. But yeah, we can't do that yet in C++26. Equally, if it throws, the size and context are unchanged. This is also not something we can do in C++26. Have post conditions on irregular returns, like when it throws an exception. We also can't express class invariants yet, which would be very, very useful here too. And then, of course, very importantly, there are preconditions like these 2 iterators represent a valid range, which you don't even know how to express in C++ today. Right? So C++26 contract assertions are very useful, but they only represent part of the actual plain language contract. Right? So this is the last slide I have on contract assertions. what they are and what they're not, it's kind of really important to understand like where they fit in when we talk about these things. So they are a standard syntax to express a subset of the actual plain language contract. They provide optional runtime verification of that subset. You can mitigate violations, when they are caught at runtime, which means it is a completely redundant thing if your code is correct, right? It only is useful or does something useful if your code is not correct, if you have a bug. They are, more than anything, kind of just an evolution of assertion macros, right? They are not macros, so that gets rid of lots of problems with the preprocessor. They are independently suppressible, so you have more granularity. You can put them on declarations, which is really, really good because then your tools can see it, the human can see it. They're portable, scalable, configurable. So your static analysis tool can see them if they're on the declaration. Your IDE can see them, can display a little bubble saying, hey, you violated a precondition here. And then also something that's really, really interesting is that contact assertions make it very good input for an AI if it wants to make sense of your code. If you have pre and post conditions on a declaration, the AI, large language model, will much better be able to reason about your code, and we have evidence for this. This is a very new thing. This is very interesting. But I'm not going to go into this here. What I'm just going to mention is what CSS contact assertions are not, right? So they are not a tool for error handling. They're a tool for bug detection. They're also not a tool for input validation. If you get bad input, you want to handle that always, not with like redundant annotations that you can turn off, right? They're also not a tool to test the condition that's not part of the plain language contract. They are only there to test something that's part of the contract, something that is for expressing when a program is correct. They're also not a tool to prove correctness mathematically, because that's not in general something you can do in a scalable way, but they are a tool to improve it, because every assertion makes it more likely that a bug will be found, and it makes it more likely that your program then will be correct. So you should add as many assertions as you can everywhere in your code. And finally, contact assertions are not a tool to provide language level guarantees, like my operator correct will never have you be, because they're not about that. They're not about language level guarantees. They're about redundant correctness checks that you can turn on or off. Now, that's a little bit controversial, and actually we will talk about this a bit more. And we will also, hopefully in CSS 29, get tools like, but this assertion always needs to be enforced, which then gives you some level of guarantees. But we don't have that in CSS 26, because that's kind of not what this feature is for, right? So this feature targets correctness above anything else, and not directly these things in a way you would think. So let's talk about this a little bit more, because the problem is that when people talk about safety, as John already said in his talk, they mean very, very different things. And I think one of the reasons why we have all of these debates, but are contracts a safety feature? And people say definitely yes, and other people say definitely no, because they don't provide guarantees, is because very different people have very different ideas of what safety actually means. And it turns out there's actually at least 4 completely different definitions of safety that people on the committee have used over the last couple of years. And so we end up talking past each other all the time. And I think that's part of the reason why there's so much controversy about some of these things. So there's one definition which, for example, Dave Abrahams has used in his keynote at CPP Now, I think last year or the year before. A safe operation is one that cannot cause undefined behavior. A safe language has only safe operations. And that's what kind of a lot of the discussion is focusing on, that definition of safety. There's a completely different definition of safety, which is the definition that most people in the real world actually use and actually mean when they say the word safety, which is something is safe if it doesn't cause harm to people, equipment, or the environment when something goes wrong. So that is what we actually mean most of the time if you're not on the C++ committee by safety. There is a more formal version of this, which is actually, if you go to this URL, which is the kind of founding paper of SG23, which is the Safety and Security Study Group on the C++ committee, when that study group was started, they provided this definition of safety. Safety is an emergent property of systems measured statistically and regulated by policy. The prerogative to decide if something is safe is usually reserved by governmental organizations. So that's kind of the working definition that you're working with when you're in safety critical environments, like you're making cars or airplanes or, I don't know, military technology, that kind of stuff, or medical perhaps. This is kind of the definition you're going to be working with. And then there is yet another definition, which a bunch of people like Chandler and Sean Parent have used in their recent talks about safety, which is kind of more on the UB side of things, but it's a bit more general. It's about guarantees in general. So safety is characterized by invariance or limits on program behavior in the face of bugs. So it's kind of a little bit like this UB definition. It's like, what guarantees do we have if something goes wrong, what the worst case is? But it's a little bit more generic than just focusing on UB. And then, Sean Parent had a more kind of formal definition of this in his keynote last year. So there's very, very different definitions. And my suggestion is that we just stop using the word safe, because it just means so many different things to different people, or at least we always put it in quotes, and instead we actually say what we mean, right? So these things have terms, they have names. So when we talk about, a programming language or a program not having UB, instead of saying it's safe, let's say it doesn't have UB, right? That is a much more precise way of talking about it. If you're talking about safety in the sense of it's not going to explode and harm somebody, we're talking about functional safety, right? So let's talk about these things and call them by their names, and maybe just not use the safety word at all. And so here on the right-hand side, there's also a little bit of a distinction we need to make, whether we're talking about a program that has these properties, or we're talking about a programming language that provides these properties for all programs that you can express in this language, right? So again, we need to be a little bit more precise here. But the really, really important distinction is that the types of safety that are here on the right-hand side are guarantees that can be provided within some kind of logical framework or program, or maybe within a language specification. And you can at least, with some trade-offs, but often you can enforce them in the compiler or with tooling. There are things that a machine can reason about. Whereas the safeties here on the left are statistical properties, right? They're addressed by regulation and assurance, which means testing. And they're things that only humans can reason about, because the machine doesn't know if something is safe, right? And so there's kind of this tension here, and I think it's really important that we talk about what we actually mean when we say safety, because then we're going to talk past each other maybe a little bit less. And in particular, I think often people, when they talk about safety, they mean one of these kind of two extremes on this spectrum here. They either talk about functional safety, or they talk about absence of UB, which are completely different things, right? So they are related, right? And I hope you all agree that absence of UB is a good thing, right? But it's not a necessary condition for functional safety. People have been writing safety critical code in C++ for decades, and typically planes don't fall from the sky if the software is written in C++. Sometimes bad things happen, but we've been running this for decades. There's regulation, there's certification, there's all of these good engineering practices, there's tooling, and there's people who want to abandon C++. There's other people who say, oh, we want to keep using C++. It provides the right trade-offs for us, right? So it is possible to deliver a functionally safe product in C++ if you apply all of these other engineering practices, and mostly if you test it in that kind of a realistic environment, right? This is what people have been doing. This is what all these safety regulations are about. Absence of UB, of course, is also not a sufficient condition for functional safety, because you can easily have safety-relevant bugs that are completely have nothing to do with the programming language. For example, imagine you have a rocket flying somewhere, and then you're calculating where it's supposed to fly, but then you didn't know that if you add 1 million floating point numbers together, you get accumulating floating point errors. And then the target is going to be somewhere completely different from where you thought, because the floating point number that you get in the end is completely different. And what you should have done is apply Cahan summation or something like this, where you compensate for the floating point error. This is something that no programming language in the world is going to protect you against. Contract assertions might. Testing definitely will, right? And it has nothing to do with UB at all. And then security is something slightly different. A program is secure if it's not vulnerable to malicious attacks. So it's about, when safety is about things accidentally going wrong, security is about a conscious malicious attacker trying to break your product to do harm, right? And so absence of UB seems to be a necessary condition for security, because if you have UB, you have these vulnerabilities that people can exploit, and you can't really reason about them. But absence of UB, again, is not sufficient for security. And actually, many of the big security vulnerabilities that we have seen in the last few years have absolutely nothing to do with UB whatsoever. And there is also this figure that is cited, that how various big companies like Microsoft and Google have found that about 70% of CVEs are caused by memory safety bugs, and I think that is kind of accurate. That's what they're seeing. But Herb Sutter had a blog post about this, good article about this about a year ago. It doesn't mean that if you make C++ memory safe, 70% of CVEs are going to just go away. It just means that attackers are going to find a different thing they're going to be focusing on, because they're like a gas, right? They fill all the available volume. So it brings us back to this diagram. What is a good program? And if you focus on these three properties, it turns out that it's actually not like this. It's more like, we saw that safety is actually different things, and we could focus on those two in particular. And there's like other potential definitions somewhere in between there as well. And that's also still not accurate. And it's kind of more like this, where they are kind of all overlap. And then correct programs are the ones that have all of these properties there. And whereas things like remove undefined behavior from the language is trying to get all of the code in the red bubble, contracts, which are about expressing correctness expectations on a program that only the human knows, are about moving more of the code into the very middle, into the correct bubble here, without ever being able to move all the code there, right? So there's a kind of very different complementary approaches to this problem. All right, but let's talk about UB, because that is kind of a big focus of this whole debate. Even though it's just part of the picture, as I hope now is clear, it is a pretty big part of the picture, because of course in C++ we have a lot of UB, right? So if you have UB, then a nasal daemon could emerge and make your life difficult. And when you talk about UB, something that I regularly see on the internet is this. People are asking this. Why don't you just make all the undefined behavior ill-formed instead? And it's actually not a stupid question. I think it's a really interesting question. And the answer, of course, is you can't just do that, right? So it turns out UB is a runtime property, and you simply cannot prove at compile time whether a given C++ expression will have UB at runtime, because it depends on runtime values, and you just don't know at compile time, right? So there are special cases where you know that this will be UB. There are special cases where you know it will not be UB, but for the vast majority of code, you cannot tell at compile time. And then you have a choice, right? Either you reject the code because you don't know, and that basically will break almost all the C++ code out there, or you accept it, and then you have to do something else. And this is kind of what I want to talk about here. And memory safety is a big part of UB. And it's one that, like, as we saw in the very beginning of this conference, there was this little introduction, which is what all of these government regulatory bodies are focusing on a lot to improve memory safety, because it is a big problem. And we actually know how to solve this problem. This is not like a new thing, right? This is very well researched, and we kind of know the space of like how we can approach memory safety in a programming language, right? So there are basically runtime and compile time approaches. At runtime, we can do garbage collection. We can do reference counting, right? So that's Java, and like Swift 6.0 has automatic reference counting, right? So those are the two major runtime approaches. There's also another approach, which is something we are doing in C++, which is instrumentation, right? So you can instrument your code with memory sanitizer and address sanitizer and all other tools like this, which are going to add instrumentation There's also dialects. I recently learned about Phil-C. There is other ones. I think there's one that Apple uses in their bootloader, and there's like all kinds of these dialects where you kind of just add instrumentation. Like every pointer is a fat pointer that carries information about what it points to. Is it within its lifetime? You know, what type of data is it pointing to? So that, of course, has a big runtime cost, right? And sometimes the trade-offs are favorable. Sometimes you will only use it in testing. Very often you will not be able to do this in production. And then there are compile time approaches. And they basically fall into a spectrum of banning any kind of mutation, like pure functional languages. They're all memory safe by design, right? If you cannot mutate anything, you cannot really run into memory safety issues. And then there is the Rust approach, which is you allow mutation, but you enforce the law of exclusivity, which means you either have multiple const references or pointers to the same thing, or one mutable reference and no other references to the thing. And you enforce that, right? And so that's what the Rust borrow checker does. And then those two approaches are kind of the two extremes, and there's a spectrum. There's other approaches like high-low, mutable value semantics, which is kind of in between. My point is that this is nothing is new here. Like we know what the solutions are, and we also know that enforcing the law of exclusivity is not just something that just magically will make all the UB go away, because we still need raw pointers and references for a lot of basic functionality in C++ and also in other programming languages, right? This is why unsafe Rust exists. Because you need to be able to do all of those things, right? You need to have double linked lists. You need to have custom allocators and other things that you can only implement with raw pointers, right? And so some of these things you can only implement with unsafe code inside, but you can have safe interfaces to them, right? This is kind of the Rust approach. Those interfaces will necessarily look different from the interfaces we have in C++ today. For example, std_vector has a function called data, which leaks a pointer to its guts, right, somewhere, and then you don't know what's going to happen with that pointer. That's not a safe interface, so you would have to redesign those interfaces. And then there are things down here which just you cannot even use in a safe way. Like there's no way to contain the kind of pieces of code that are memory unsafe. If you're calling into a C API like in your system, then you just cannot provide any guarantees about what's going to happen. Sometimes you can wrap it into some kind of safe interface, sometimes you can't. And anytime you manipulate raw bytes, or you have raw pointers to somewhere, or you have like a call into any existing C or C++ code, you can just not provide any guarantees at all. And that's just a fact of life. We need to deal with this. And so this is where kind of what's the fundamental difference is here between Rust and C++. So Rust is kind of this thing where most of the code is safe Rust, which has no UB, and then inside these like things, whenever you implement a certain data structure, for example, that you need raw pointers to implement, you have these localized bubbles where you have unsafe Rust, and that code may have UB, but because it's local, you ensure it's correct by staring at it long enough, or by other means. But if you run into a problem, you know that the only parts of the code that can have UB are those very localized, contained ones. Whereas in C++, we're kind of in this world, right? Today, this is where we are. And getting from here to here is not really something that is really something we can do, right? So it kind of feels like we're doing this. And I think that's just not really going to work. I think we need to be a little bit more realistic. Where we can get to is to go from here to here, where it's kind of the other way around, where we have bubbles of code where we can reason about they not having UB because they're written in some new, maybe safe subset. And then the other thing that we can do is all of this code, we can kind of reduce the amount of negative impact that UB has without being able to reason that there is no UB at all. So it's kind of, we're not going to get to where Rust is ever, because, in my opinion, because that's just kind of not, there's no migration path there if you are sitting on a big pile of legacy C++ code, but there are things we can do to improve, right? And so to reduce UB, there are things that users and companies and regulators are already doing. The most important thing, of course, is testing, 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 good engineering practices, education, coding guidelines, tooling. Static analysis can catch some UB, sanitizers can catch UB. There's compiler options to turn UB into non-UB, right? But then there are things that the C++ committee can do, which is systematically address UB in the standard. And this is really what I want to focus on for the rest of this talk. How do we do this? So we have actually been addressing UB in the standard for a very, very long time, but it was not really in a systematic, holistic way. It was in a kind of case-by-case basis way, right? So for example, in C++ 20, we introduced implicit lifetime types, which means if you have a rule pointer to some array of bytes that came from somewhere, and you then reinterpret cast that to a pointer to a struct, that's UB, right? The compiler can optimize that away and make your program do whatever. And in C++20, we said, well, if your type has certain properties, like you can trivially construct it, et cetera, then actually we're going to start the lifetime of that object. And there's going to be an object there, and it's no longer UB. In C++23, we fixed another trap there where you could have UB if you don't know how kind of lifetime rules for temporaries work, and if you have a range-based for loop, and the range in the range-based for loop produces a temporary, then that temporary actually goes away before you go into the body of the loop, and then again you have a dangling reference, you have UB. So we fixed that by extending the lifetime of such temporaries. And now in C++26 we have uninitialized reads in some cases, like automatic variables of built-in type. Reading uninitialized values is no longer UB, right? So those are case-by-case kind of improvements, which are good, important, and provide a lot of value and make C++ safer and more secure. But it's really not enough to do this on this case-by-case basis. We need a systematic, holistic approach, right? We need to look at all of the UB and have a plan for how to address all of it. I think this is what we need to do if you want to, have a C++ standard that people still use 10 years from now or 20 years from now, right? We need to have a story, and the story is not going to be we're going to turn C++ into Rust, because if what you want is Rust, go and use Rust. But there needs to be a story how we want to address the challenges we have while not losing the benefits that C++ has, the most important one of which is backwards compatibility with billions and billions of lines of existing code that the world runs on today. So the committee has been looking into this more intensively, more recently, and so now we have this white paper, core language UB white paper that we're kind of assembling. Herb and Gasper are the editors of that, and a lot of other people are contributing to it. And so there's not much content in there yet, but this is something we're going to be hopefully focusing on over the next year or so. And what I want to talk about in the rest of the talk is a paper that I co-authored with Joshua Byrne, where we provide a contribution to this white paper. So this poll here, this is from the committee. Earlier this year, we had a committee meeting, and the evolution study group encouraged that this is what's going to go into this white paper, a systematic treatment of core language undefined behavior in C++. With these different approaches that could accomplish this. Erroneous behavior profiles and contracts. And so in this paper, which is targeting this white paper, which we hope is going to be merged into this white paper that I'm going to talk about for the rest of this talk today, P3100, we are targeting erroneous behavior and contracts. We don't talk about profiles. There's a bunch of other people talking about profiles. So we're kind of doing the complementary thing. We're talking about the other tools here. And so the goal of this paper that I'm going to talk about for the rest of this these 90 minutes I have today is a standardized framework for runtime detection and mitigation of undefined behavior across the entire C++ language. So it's an ambitious project, and what we want to do is we have that part already. We enumerated all cases of explicit core language UB in C++. Right? All of the UB in the standard, we looked at the entire standard, literally grep undefined, and looked at every single case and categorized them. So when I say explicit, I mean when the standard explicitly says that something is undefined, we also have implicit undefined behavior, where the standard just doesn't say anything about what a particular construct should be doing, and then it's kind of implicitly UB. And this is not something we can do anything about, because we can never be sure that the standard covers any program you could write, in C++. But whenever we discover a case like this, then it's a wording bug. Then we need to fix it, turn it into explicit UB, and then think about how to turn it into non-UB. So here we're talking about explicit UB, and we're talking about core language UB. We're not talking about UB in the library. There's lots of UB in the library. For example, vector operator square bracket with an out-of-bounds index is UB today. The appropriate tool for that is a library hardening, which is another exciting thing we're going to get in C++26, where you can have some implicit checks there in the standard library that you can turn on, which libc++ has been shipping now for quite a few years, and now we kind of formalized it in the standard. But that's library. I'm not going to talk about that. I'm going to talk about core language. So we enumerated all cases of core language UB. We give them unique identifiers, and we're actually going to be able to refer to them by name from the standard document. So that's going to be very useful. And we're going to have an annex in the standard that lists all of them and with those identifiers. And in this paper, we grouped all of these cases into 10 categories. And we classified them according to a bunch of criteria which the white paper is calling for. So the white paper says we should look at all UB and categorize it along those lines. Is it relevant for security? Is it locally checkable? How expensive is that? Can we define some well-defined behavior instead of the UB, et cetera, et cetera? So we have done all of these things that the white paper is calling for in this paper P3100. So we kind of have done the work there, and I want to talk about that a little bit. So we have a proposal with wording and everything, how to specify in the C++ standard runtime checks and well-defined replacement behavior in all cases where this is possible for the UB that we have in the language today. So we found, and I think this is a good time to actually have a break, because then for the rest of the talk, I'm going to talk about how we have done that, right? So how have we addressed all of the 81 cases of explicit language UB in the C++ standard. So if you want to hear about that, let's have a break now and then talk about that afterwards. Thank you. Thank you so much for coming back for the second half, where we looked at all the undefined behavior in the language and tried to figure out what to do with it. So that's exciting, right? So you found 81 cases of explicit language UB specified in the standard. And when I say case, I mean one sentence in the standard that says something is undefined. So there's different ways you could splice this up. And of course, if there's one sentence that says the behavior is undefined, you could split it up into different cases. But we kind of wanted to have this mapping of one entry in our table or in our list maps to one sentence in the standard. That's helpful, which is why we kind of did it this way. Whenever the standard says something is undefined, we count it as one case. And so we have 81 of those cases, and we grouped them into 10 categories. And so those 10 categories are these, and you might recognize some of those. Initialization, obviously reading uninitialized value is UB, right? Bounds, type and lifetime, arithmetic, threading, sequencing, assumptions, control flow, replacement functions, and coroutines. And so you might wonder, why is type and lifetime one category? Why didn't we say type UB and lifetime UB? And the reason is that in a lot of places where the standard says something is UB, typically this is something about like a pointer or reference that needs to reference an object of the right type and within its lifetime. So it's kind of both of those kind of munched together. And some UB is more about like the type when you talk about aliasing and things like that, and other things are just about the lifetime. For example, what you can and cannot do in the initializer list of a constructor or whatever. But most of the UB in this category is kind of talking both about the requirement that the pointer points to an object of the right type and that the object is within its lifetime. So you can't really separate them, at least not in the way we sliced it up. So that's why type and lifetime is one category. And so you might ask yourself, okay, how many cases of these 81 are in which category? So which one do you think is the biggest category here, the one with the most cases? Initialization, okay. Anybody has a different idea? Bounds, okay, no. So turns out 51 out of 81 cases are type and lifetime, right? So the vast majority are type and lifetime. There's 5 cases of initialization UB. No, there's 1 case of initialization UB. There's 5 cases of bounds UB. And there's 51 type and lifetime. There's 9 arithmetic. And all of the other ones have just a handful of cases. So it's not a very even distribution. So more than half of the UB is type and lifetime issues, right? And so those first 3 categories are what is commonly associated with security vulnerabilities, which is 70% of the cases. The other categories typically are not associated with security vulnerabilities, like race conditions, for example, but they are associated with real bugs that do real damage in the real world. So we should address them anyway. So, and then, as I said earlier, maybe I should go back to the slide quickly because we had this break. Just to remind you what the context was. So the white paper was asking for all of these things, and we answered all of them in this paper. So we enumerated all the UB, we gave them identifiers so you can refer to them, we grouped them into 10 categories, and then we classified them according to all of these criteria, and then we have a proposal for how to address it. So we're now going to talk about the different criteria. And so one criterion is which of these cases of UB are efficiently locally diagnosable? And that is a complex question, so we split it up into 4 slightly easier questions. Which cases of UB are diagnosable at all, in principle? Which of those are diagnosable at compile time, and which are diagnosable only at runtime? Does this diagnosis require non-local information? And by that I mean information that you don't have when you compile this piece of code on its own. Information that's not available within the kind of C++ abstract machine. Information that you would have to add instrumentation to your entire program in order to have that information, in order to be able to diagnose it. And then finally, what is the cost of such a diagnosis in terms of runtime and binary size? So those are the 4 questions we're going to look at, and I'm going to just gloss over it because you have 81 cases of UB. Each one of them is really, really interesting, so I could talk for a whole day about this. But there is the paper, P3100, so go off and read it. It has like all the details. Now I'm just going to give you a very rough kind of overview. So diagnosable at all, and turns out the vast majority are, in principle, at least diagnosable. In principle, there is something you can do, at least in theory, to figure out if that case of UB occurs in a given program. Some of them are not. If you have an assumption that is false, that's UB, and you can diagnose it by just evaluating it and see if X is false. But the problem is that you cannot prove that X has no side effects, and so if you evaluate X, you could actually change the state of the program, and then you didn't verify the correctness of the program you had, you verified the correctness of another program. So it's not like a false assumption is not diagnosable in principle in all cases. Same thing with UB because non-trivial infinite loops, like to figure out in general that you have one requires to solve the halting problem. And there's also 2 cases of UB where it says, if you have a replaceable function like user-defined operator new or delete, it's not allowed to do this, it's not allowed to do that, and those are also undecidable things. But the vast majority of UB is actually diagnosable. And so the next question is, which of those we can diagnose at compile time? Guess what the answer is? None. So it's also not quite true, actually, because there are special cases that you can diagnose at compile time, right? So obviously, if you, for example, have a function and you're dereferencing a null pointer, you have like a null pointer, and then in the next line of code you dereference the same null pointer. Of course, a static analysis tool can see this and tell you you're dereferencing a null pointer there, and you can reason about that at compile time. So that's a special case where you can tell. But if the tool doesn't see like in the second example, doesn't see the value of the pointer at compile time, then there's nothing you can do. This is the same case of UB in the sense of, a pointer needs to point to a valid object if you dereference it. And another example is maybe the compiler or static analysis tool sees that your you're dereferencing the null pointer, but maybe it doesn't know whether you ever call this function, right? If you don't call it ever, then it's not UB. Or maybe the null pointer dereference is in a branch, and if it's sufficiently complex, you again cannot say if that branch is ever going to be executed. And then it could even be something like people use null pointer dereference as a implementation of still unreachable, right? If you want to say deliberately this branch is never going to be executed, I just want the compiler to optimize it out, you can put a null pointer dereference there. That's not a bug, right? If you know that that branch is never going to be hit, it's not a bug. So you cannot just make it ill-formed. That's not something we can do. You would break valid, correct code if you do that. And so again, it's this thing where there are special cases where you can prove something, but you cannot do it in a general case. So do you want to have false positives or do you want to have false negatives? And if you run an extra tool on your code, like a static analysis tool, you probably want to just find the things that you know are bugs. You don't want to have false positives because otherwise people are not going to use your tool. And similarly, if we change the standard, we don't want to break existing correct code. So we cannot typically do anything about any of this UB at compile time in a general case. Now, which of this UB is diagnosable at runtime? And turns out some is diagnosable at compile time locally. So if the compiler sees this code, it could insert a check saying, does this occur? And this is 19 out of 81 cases, so it's a bit less than a quarter. There's 6 more cases where this is possible sometimes. And we already saw that there's 4 cases that are just not checkable in principle. But then 52 cases, which is, I don't know what this is, like 70%. A compiler could check that, but it requires instrumentation, which is potentially very, very expensive. Right, so that's all of the type and lifetime stuff. And today, doing this at runtime requires global instrumentation, like sanitizers or these like extra dialects that have fat pointers and all of that. In the future, we might be able to do this locally, which is not something that exists today, but this is a really cool idea that Gaspar Asman is going to talk to us about later today. So I encourage you all to go to his talk, which is going to be this afternoon in this room. And so this is, if you break it down by cases, this is when you break it down by category. So a lot of stuff just isn't locally diagnosable. Arithmetic UB is locally diagnosable because it's typically stuff like, if you convert one number to a number of a different type and the new type cannot represent the value of the old type, then that's UB. You can look at that value. You can inspect the bits and bytes of that value and reason about, if you know the type representation, whether that's a valid value. So that can be locally diagnosed. Similarly, sequencing, this is very expensive, but you could theoretically inspect every possible sequencing of operations and say, if anything goes wrong there, if any of them, this is the I+++++ I case, right? If you have unsequenced operations that modify the same memory, that's UB. You could try all combinations and see at runtime if they access the same address. Probably very expensive, but you can do it. All the other UB requires instrumentation or is not possible at all. So for those that are locally diagnosable, there's also the runtime cost of the check itself. So, for example, the easiest one would be if you insert a check that just says, if you get here, you have UB, right? So this is something like user-defined operator delete is not allowed to throw an exception, and if you do that, you can just say, well, assert false. If you got here, this is bad, and this has pretty much no runtime cost unless you hit the UB. I mean, okay, it could impact the optimizer, it can impact code size, so it will maybe impact the kind of data cache misses or something like this, but it mostly has no overhead unless you actually hit the error. The next most expensive would be a null check. There is UB, which is, is this a null pointer? That's a very cheap check that optimizers are very good at optimizing out. Then there's integer comparison, which is a little bit more expensive for bounce check, row array bounce check. And then, it gets more and more and more complicated. And then there is UB where you'd have to check if two ranges overlap based on the addresses. So there's more operations you have to do. Then there's some operations where you would have to do a modulo operation in order to figure out if it's UB. When you talk about it's UB if you placement new an object into memory and that memory is not suitably aligned for that type, for example, that's UB. You need to do some modulo operations. Probably that's cheap if it's a power of 2, so it's probably still okay. But anyway, so there's a growing kind of runtime overhead for these checks if you want to insert them. And then one type that will probably be a bit more expensive is if you want to know if you have UB because you messed up your integer or floating point conversions, and then you have to actually go and see what is the bit representation of this type. You might have to do some bit masking or whatever. So this is compiler magic that will have to happen if you want to check this at runtime, which will probably be expensive. And then you have to multiply that by how often you would have to do the check. Now, for diagnosing things that are not locally diagnosable, like pretty much all of the type and lifetime stuff, it doesn't really matter how expensive the check is because the overhead will be dominated by the extra instrumentation that you need to add, like what a sanitizer does, right? It adds lots of instrumentations. It makes all the pointers into fat pointers that track a lot of more stuff. Turns out, if you want to, at runtime, detect all of the UB in the language that you can, in principle, detect, you would have to track all of this stuff just for the type and lifetime UB. This is a lot. I'm not going to go through all of this in detail, but you would have to for all storage, for all objects, everywhere in your program, just track lots of properties for the entire program, right? So that's going to have an order of magnitude runtime overhead probably. So it's not something we can do really in every scenario. And then there's other things like threads, right? In order to diagnose at runtime whether you have a race condition, you would have to track all potentially concurrent accesses to memory and from what threads they happen, and that's not something that would be feasible, right? For a few others like control flow and for coroutines, you would probably have to store some additional state there associated with every coroutine handle. That's probably more on the doable side of things. Excuse me, but that would be again overhead on every coroutine, regardless of whether it has UB or not. Now, the next question is, for which of this UB we can define what we call well-defined fallback behavior. So let's say the condition under which the UB occurs has occurred, right? So you have a bug. So what do you do then? You could terminate. But if you decide to continue, or if you didn't insert the check because it's too expensive, you keep going, and what you could do is you could just replace the UB with well-defined behavior, but behavior that is no longer UB. So you have a bug still, you're executing buggy code, but this is kind of what the Lampert safety stuff talks about a little bit. You put kind of a limit on how much damage this code can do by no longer making this code unbounded, undefined behavior. And there's two ways of doing this. You could say that the behavior is well-defined but erroneous, which means it's still a bug, or you can say we just replace the UB with other behavior that we now say that's just the behavior, that's just correct now, right? And so you want to be careful with this because you're going to be typically masking the bug. There are a few cases where probably that makes sense, but in most cases you want erroneous behavior. And if you replace undefined behavior with well-defined behavior, that cannot depend on knowing whether the error has occurred because you don't know that at compile time, right? So you have to, the compiler has to generate instructions to do something concrete at compile time, but you don't know if the error has occurred at compile time because that's a runtime thing. So the new behavior that we replace the undefined behavior with cannot depend on that, right? Because that's unknowable at compile time. And so we looked at all of the 81 cases of UB and tried to figure out for which of those we can do this. We can just define the UB away, and then so we can do this unconditionally for 14 cases. And there's 3 more cases where we can do this for the case where the operation operates on built-in types, like integers, floating point numbers, booleans, but not in other cases. But in something like 80% of the cases, there just is no meaningful replacement behavior. And this is something that is a little bit unfortunate. This is basically everything that has to do with, for example, the memory safety stuff. If you dereference a pointer that points to memory that you shouldn't be accessing. There's all of this instrumentation you can add to check at runtime whether that occurred. But once you diagnose that there is UB, like the only thing you can do is terminate, right? There's nothing there's no behavior you could have instead of dereferencing a pointer to memory that you shouldn't be accessing. What should that dereference return? There's no meaningful behavior here that you can replace this with. You can just get out of there. That's the only thing you can do. So there's no well-defined fallback behavior for the case that you want to continue executing that code. So this well-defined fallback behavior is definable for 17 cases of UB, 14 of them unconditionally. And in all of these cases, you found that we should define it as erroneous behavior, which means it's still a bug. So a tool can still say, don't do this. And these are the specific behaviors, so I don't have time to talk about every one of these 17 cases. This is all in the paper. There's like a big annex. There's like pages and pages and pages of like, it lists all the UB and like for each one of them what the proposed fallback behavior is. We're going to talk about a few examples in a minute. But basically, the specific behaviors are return an erroneous value, or just, if for the unsequenced operations, just do one order. For assumptions, you can say, just ignore them, then you're not going to have UB. And then race conditions are interesting because you could define fallback behavior to say a race condition is not UB. It's just, you're just accessing the memory atomically. Like that's basically the Java model, which is still going to give you torn values. It's going to give you incorrect stuff, but it is, kind of not unbounded, undefined behavior. So this is probably not something you want to do in practice and production because it's going to have overhead. But this is something we can define as a fallback behavior to kind of prevent data races from messing with your code in unbounded ways where like things get optimized away and things break in some random fashion. So all of this fallback behavior has runtime overhead and sometimes a very considerable runtime overhead. So we cannot just say this happens always. It cannot be unconditional. We need an opt-out, right? So we can make the safe kind of well-defined behavior the new default, but you need to have a way of saying, no, I want to go back to where it was UB because otherwise I get an unacceptable performance regression, right? And so this is kind of where we then get into how do we actually specify this. And so this is the actual proposal here. So it consists of 3 parts. We systematically introduce these runtime checks. This was the first part. Then we systematically replace UB by well-defined fallback behavior whenever that's possible. And then we provide this opt-out so you can opt out of the performance regression. So the first part is something that we can leverage C++ contracts for, right? So reminder, we saw this in the first half of the talk. We have, you have these preconditions that you can write on your own code, right? And so they're evaluated with one of these 4 semantics. And if the predicate is checked and check fails, you call the contact violation handler, and the program may or may not be terminated depending on which of the 4 semantics you chose. And then you can replace the contact violation handler at link time and have your own handler that logs or does something else that you want. And so we have that in the C++ 26 draft, and we can just leverage that to introduce implicit checks to guard against core language UB, right? So these preconditions and postconditions that you wrote, we now call them explicit contact assertions. And our strategy is that whenever it is in principle possible to insert a runtime check for a case of core language UB, we specify that check as an implicit contact assertion. So it is an assertion that you didn't write, that the compiler just inserted for you, and that's going to guard against the undefined behavior. And so we can apply this wording transformation across the entire standard. Whenever it says, if X is not true, the behavior of operation A is undefined, we can say operation A has an implicit preconditioned assertion that X is true. It's just a wording transformation we can apply across the entire standard. And so then, yes, so you get an assertion that is just inserted implicitly, for example, a bounce check. And we do not require an implementation to provide all possible checks because one of the 4 semantics is ignore, and that's always a valid choice. So a compiler can say, well, I don't know how to insert checks against pointers that point to nowhere, but but I'm just going to always evaluate those assertions with the ignore semantic. And the only thing that the compiler has to do is it has to document that, right? So we require that because that's what implementation defined means. The implementation has to document what it chooses. And if you do this transformation, then what we're doing is we're taking all of these checks that compilers and sanitizers already implement today, and we kind of provide a framework to talk about them and to make them part of the C++ standard. So we enable things like sanitizers, for example, to use the same callback API as contract assertions do in C++26. So we have one API that all the tools can agree on. We codify names and categories for this UB, and we can integrate that with all of these other things. So yeah, if, for example, GCC has a flag to say, we're going to trap on integer overflow, then that is the quick enforce semantic for this assertion, right? So this is kind of going to all be part of the same framework rather than just vendor extensions that use different vocabulary and different things. So the second part is systematically replace UB by this well-defined fallback behavior whenever possible. So we saw this is only 17 cases out of 81. So for the other cases where it doesn't exist, we're going to do this transformation. If UB would otherwise occur, we would say that operation A has an implicit precondition assertion that X is true. Continuing execution past the violation of this precondition is undefined behavior. So if you ignore it, you're just going to get today's behavior. But if you have fallback behavior, we then just say, well, if you have a violation, you keep going anyway, maybe because you ignored the check, because you can't pay for the cost. Then you get this well-defined fallback behavior instead. So you no longer have UB, right? And since this has potentially very high runtime overhead, we can't just force this onto the entire community. We have to provide an opt-out. And we can do this very, very elegantly within the contracts framework. So I said we have 4 semantics, and we have 4 semantics in C++26 today. But when I said we have 4 evaluation semantics in principle, I lied. There's actually a 5th one. It's not part of C++26, but it's kind of there conceptually. The 5th semantic is the so-called assume semantic, which is do not check the condition, but assume it's true. And if it's not true, the behavior is undefined. And this is how all of the UB behaves today in C++, right? So, and this is kind of the tool we need to have this backwards compatibility. So we do not propose to allow assume for explicit contract assertions, the ones that you wrote pre and post. This was very controversial. People have proposed this in the past. This is one of the reasons why contracts didn't make C++20, because that feature was there. People said it's unsafe. Not proposing that. Only for implicit contract assertions, which are all UB today anyway if they're violated, right? And so we just have a way of naming the behavior today. The behavior today is that all of these implicit assertions, they are assumed, right? And so you get UB. So we now give that a name. We say it's called assuming the implicit contract assertions. That's just the name for the existing behavior, and you're going to have that available as an option if you need to kind of like go back to the old behavior to prevent performance regressions. You now have a name for it, but you also have the 4 other options which are safer, right? So this is a bit abstract maybe. So let me talk through a few examples to make it maybe a little bit more clear how this actually works in practice. So let's first talk about the first branch here, which is, there is no fallback behavior. One example is out-of-bounds area access, right? So let's assume that we have a built-in array, and let's just assume for the sake of argument that the compiler knows the size of this array. And so then, you have potential UB here if, so the number, if the index is bigger than 4. And you don't know if it is at compile time because it's read in, it's supplied by the user at runtime. So there's nothing you can do at compile time. But you can insert an implicit contract assertion. And the way it works is that you pretend as if this array indexing operation here was happening through some kind of, notionally, through some kind of like magic compiler generated function like this, which actually performs the dereference, right? And then you say, well, this function now has a precondition like this, which is an implicit contract assertion. And that can now be ignored, enforced, assumed, etc., right? And so the user can choose which one they want. And so here, ignore would be the status quo, and then you get UB in the next line. Enforce would be basically what address sanitizer does. Quick enforce for just the ones where you know the bounds at compile time would be, for example, Clang's f-bound safety flag that I think they're still working on that. I'm not sure they've released that already. But like, there's all of these different approaches that vendors already do to address these things, and we give them names. You make them part of one framework, one unified framework. So this is that, and then there's the other branch, which is we have fallback behavior. And the typical example here is the signed integer overflow. So if we have signed integer addition, we just pretend that the addition happens via this kind of built-in operator, which now has this implicit precondition assertion that the addition does not overflow, and this is the expression. And then we say that in the body of the function you have some well-defined behavior, so it will return some integer, right? Erroneous but not undefined. And then again, that maps to things we have today. Assume is the status quo. The compiler is allowed to optimize based on the assumption that this is always true, and if it's not, then your entire branch might be optimized out, or you might get nasal daemons. Ignore is well, just return some integer, right? And don't check this expression, but just return a valid integer, which is what, for example, GCC's wrapv option gives you today. It just wraps around. That's one way of implementing that. Enforce would be ubsan, which calls a handler, prints out what the error is, and then terminates. And quick enforce would be GCC's ftrapv flag, which you can also use today, which checks this condition and then traps immediately. Just basically terminates your app immediately when that condition is false. So those are all the cases here. And then you get a few additional features, hopefully in CSS 29, when we have labels, which is a powerful new extension. Where you can do things like this. I don't think I have time to go into much detail here because I only have 15 minutes left, and there's other stuff that I want to cover. So maybe just very, very quickly. So you will be able to do things like, there's a category FUB, which is bounds. Then you will be able to say, oh, I have an explicit precondition assertion, and that one is also in category bounds. And you can have a global flag that says, turn on all the bounds checks. And you can also have local encode control. You can say, for example, in this function, always enforce all the arithmetic UB, or like observe the bounds UB, or things like that. And so if you do this systematically, we will not, maybe get here, but we will get from here to here. So we will be able to write these bubbles where we know, like, we have runtime checks here that guard against the UB. And in all of those cases where we can't enable all the checks, or maybe the implementation cannot provide all the checks, we can at least have less UB. And this way we can address this big red blob. It will have less UB, right? So this will be an improvement. And I want to briefly talk now, this is the last part of the talk, how does all of this fit kind of into the bigger picture, right? So a lot of buzz and discussion and papers have been written about safe C++ in the last couple of years. So I talked today about contract assertions, which we have in CSS 26, erroneous behavior for uninitialized reads, which we have in CSS 26. There's also standard library hardening, which is inserting contract assertions into the standard library and saying that on a hardened library, those are always checked. That is, I've not talked about this, but this is another thing we get in CSS 26, which builds on top of contract assertions. So I talked about P3100 today, which says, let's go beyond this. And this is not in CSS 26, right? This is the future. This is this white paper we're working on. Let's go beyond this and introduce implicit checks for core language UB, and also let's introduce well-defined behavior instead of UB whenever we can with an opt-out. There's other papers here that are proposing other things. There's the language subsetting paper by Peter Bindels. There's other papers. There's obviously Sean Baxter's work on the borrow checker, which John has talked about a little bit in his talk. There's a lot of papers about profiles. So there's all of this stuff, and like, how does this actually fit into the big picture? Because I said we need a holistic strategy. And so here's how we can think about this. So I talked about all the different properties that a good program should have, and then I said, well, it's not actually like this; it's more like this, right? And so I think there is kind of different things we're doing here. If you're doing explicit context assertions, we're telling the compiler or the machine what we as the human consider correct. So we're targeting this middle bubble there that says correctness. If we're doing implicit contract checks that are targeting kind of core language EB, then we are saying, well, we are kind of making this bubble smaller, the red one, right? And so basically the point here is that we need to talk about which part of this diagram we're talking about here. And now we're just talking about the red bubble here, the red one, right? Less UB. So how can we achieve this? And it turns out there is kind of 7 low-level tools that we can apply, and some of which I've talked about in a lot of detail, some of which I've not talked about so much. One of them is we can just remove features, right? I've not talked about this very much, but we can do this. There's a paper proposing, for example, throwing from a delete operator is UB, so we can just make that ill-formed. We can just say it has to be not ill-formed, but we can say it's just always has to be no except true, and then you just get terminate instead, which is not UB anymore. So just remove the feature of having no except false delete operator. So we make that ill-formed. Another thing we can do is we can say, well, we just define the UB away completely. We just say now it's this other correct behavior. And this is something we did for the range-based for. We just said we just are going to extend the lifetime of the temporary, and that's now correct. The thing that I have talked about is something slightly different. We say, OK, we do make the behavior defined, but it's still erroneous. And then that's the other thing I talked about a lot. We can add implicit runtime checks. And then we can do more. We can say that we define a subset of the language, right? We can say, well, we can't reason about whether this construct has UB or not at compile time, but often it does. It's dangerous, like reinterpret cast, for example. So we can say, by default, that's ill-formed. We have a safer language subset where this is just not in that subset. Like we do with const expert today, right? Like it's a subset of the language where reinterpret cast is not allowed. But at runtime, we need to have an opt-out, right? So we need to still make it allowed to write reinterpret cast sometimes, like in an unsafe part of the code, because you need that to implement certain things, right? So then we need a mechanism to kind of opt in and out of those language subsets. So that's language subsetting. It's not the same thing as feature removal. We can't just make it unconditionally ill-formed. And then we got annotations. So Clang, for example, has this thing counted by. You can put that on a pointer to say it points to a range of n elements, and then you can kind of do a bounce check even if you don't know it compile time. Otherwise, without this annotation, the array size, that's a way of kind of propagating it across function call boundaries by adding an annotation. And then there's completely new features like adding a borrow checker or adding a saturate cast instead of having signed integers that just overflow. And so those are 7 basic tools that we can use to reduce UB in the language. And 3 of those tools, these 3, are notable because they are usable on code that you cannot change for whatever reason, right? So the other tools are, they make things in a form that are valid today, which you cannot do in legacy code, or they require you to write new code, rewrite your code, or add annotations to it, which often you cannot do if it's legacy code. You don't want to touch it. But refined behavior, which is replacing UB by correct, well-defined behavior, erroneous behavior, and runtime checks, is something you can do without any code changes. Right? So this is something where you can say, OK, we're going to add these things. You can recompile your existing legacy code. It's going to have less UB. And then there's another subset here, which is these features which need to be configurable. Right? So if you replace UB by erroneous behavior, that has overhead, so you need to have an opt-out. If you introduce runtime checks, that has an overhead, so you need to have an opt-out. If you introduce language subsetting, Sometimes you need that dangerous feature like reinterpret cast. There's certain things like tagged pointers that you cannot implement without it. So you need an opt-out. So those three features need opts-out of some form, like a compiler flag or something, right? And so this is kind of the picture here. And the proposal I talked about, which is this P3100, talks about these 2 out of these 7. And there's other papers talking about other parts. I believe Gaspar is going to cover a few more things later. And there's other papers doing other things. But this is kind of the whole picture. And this is what I showed you fits in here. And now, of course, there is one more safety feature that has been talked about a lot, which people have wrote papers about, which is not represented here. Do you know which one that is? Profiles. The profiles are not in this diagram because it's been a bit controversial. Lots of people have written about profiles, but we don't agree in the committee like where they fit in. So some people say, and like some of the papers that are proposing profiles say, this is some combination of runtime checks and language subsetting. There's other people who say, oh, this should also maybe cover erroneous behavior and make like UB into erroneous behavior, and maybe different kinds of erroneous behavior even. There's other people who are saying, no, profiles should really just be doing the language subsetting part because the runtime checks we already covered with implicit assertions, which is what I just talked about. So we don't have agreement on this, but I think actually there's one way in which we can solve this really elegantly without any of these features stepping on each other's toes. We can say, well, these 3 features, erroneous behavior, runtime checks, and language subsetting, they need to be configurable. So we need to define configuration mechanisms for those things. In some way, they probably need to be specific to those features. Because, for example, for runtime checks, the configuration is, the semantics, observe, enforce, ignore, etc. For language subsetting, it's going to be something else. But profiles, really, where they fit in is here. They are basically an abstraction that sits above this and provides you sets of configuration presets. So, for example, if you have a MISRA, which is a coding guideline, which can also be enforced by tooling, then you can have a MISRA profile which combines certain runtime checks and certain language subset. And you can give that subset a name, and you can have ways in which you can enable that and disable that. And so that really is the full picture. This is how we're going to address UB and the C++ standard going forward. And I have 5 more minutes, so I just want to show you a little bit more what you can do with this, because this is only one dimension. These are the tools we have, right? But you could then put them up here and put like the different categories of UB here on the y-axis, and then you can think about which tools are appropriate for which categories of UB. And then you end up with something like this, right? And I just want to call out a few things here, going from left to right, just to give you a few examples, like a feeling for how this is really a system that covers everything that people are working on in a systematic way. So feature removal here would be something like, what I said, operator delete must be no except, otherwise it's just ill-formed. That feature removal that works for like one particular category of UB down there. Refined behavior is the range-based forfix, which is, it's just a new behavior now. Then, erroneous behavior and runtime checks, I talked about this for half an hour. Language subsetting would be something like, have a subset that excludes reinterpret cast, right? Annotations are going to be very helpful for, bounds, type, and lifetime, for example. Clang has an annotation that helps with bounds checks. There's also people working on lifetime annotations. There's people working on annotations about which types are thread safe. It's kind of similar to what we have in Rust with send and sync. So these are annotations where we can, have more information available to check and diagnose UB than we have in C++ today. And then there's new features. For example, for bounds, it would be something like, always bounds checked span. And then for type and lifetime and threading, it would be something like a borrow checker, right, which is from Baxter's work. This is a new feature, right? And same for arithmetic. We have saturate cast. That's a new feature. So these are 2 dimensions. There's actually a 3rd dimension, which is the configuration dimension. So we have these 7 tools here. 3 of them are configurable or should be configurable if you want to use them at scale. And there's all kinds of different questions here, like what are the configuration options you should have? What granularity? Like, is it an open set or a closed set? What's the mechanism to select these options? And so for runtime checks, we kind of have answered that question. We have these semantics. But a lot here in this diagram, we don't really know yet. That's actually future work. So this is where some of the papers we have about profiles or implicit checks and language subsetting kind of step on each other's toes. We need to actually nail down, which feature will be responsible for configuring which tool and in which way. And this is, I think, the kind of stuff that we'll need to go into this white paper. This is going to require lots of discussion on the committee. But I hope that this framework, this system, is going to facilitate those discussions by being able to kind of name these things. Like, oh, you have a profiles paper. You have a paper about turning profiles on or off. Okay, so where in this diagram does this go, right? So I hope this is going to help us figure this out. And I think this is what the committee is, or at least should be focusing on in the next year or so. And so I'm very much looking forward to that work happening, and hopefully then having a more safe, secure, and correct C++. Thank you very much.
Fully deserved applause, and I would like you to repeat it, please.
Thanks.
Thank you. Safety, security, and correctness for C++, a holistic approach by Timur Doumler. I just thought that maybe you could still try to squeeze his mind a bit more by at least asking 1 or 2 questions. If you're not running for dinner yet or any kind of lunch that you probably are waiting for, feel free to ask. There are 2 microphones. Tomek and Rafał are with us just to give you this opportunity. If not, please do remember that we actually gather all of these questions. We take them from the online versions, and we will be passing them on to our lecturers, to our speakers for today. But let's just give a chance, like 10 last seconds, just to look around. There's 1 question here, so maybe we could support Tomek by giving the microphone to our colleague. So there's a question just in the middle right here of the room.
Yeah, thanks.
Hopefully it's on.
Yeah, so thanks for the talk. So what I want to ask is, when you're when you work on a committee, do you consider adding new stuff as a problem to the standard? Because you're still adding new stuff and you're adding complexity, and it sounds pretty complex. And I'm pretty familiar with C++, but it's never ending. So I'm asking whether the adding complexity is a thing that you're thinking about when tackling these problems.
Yeah, this comes up a lot. Actually, I heard this opinion a lot when we discuss things on the committee, where somebody stands up and says, yeah, but this is too complex. Now I need to teach more stuff. So I would say that this is definitely regularly coming up, and every time we add a new feature, we don't just ask ourselves, is this a feature that makes sense? Is this a good specification? But we always ask, what's the cost-benefit ratio of adding this complexity versus the value that you get from this feature? Is it going to remove pain from everyday C++ programmers? And is it going to remove enough pain that it's worth the pain of learning more stuff? So there's always this cost-benefit ratio that we do on the committee. We discuss that quite a lot, especially with complex features.
Yeah, maybe one more follow-up. So you said on the Rust side, it's basically like safe by default, and on the C++, it's kind of there are some snippets that parts that are safe. Do you think that I can today use C++ in standard library and kind of decide to not use unsafe stuff and get a maybe worse performance, but still a safe language? Or do I cannot do this, like in C++?
Right. This is a deep question. How much time do we have? We have like 8 more minutes, right?
We have run out of time, actually, but you can still meet in the corridors and just talk it over.
Cool. Okay.
It's up to you guys.
I have a lot to say on this topic. This is a very good question.
I knew
it's
it would
not a
happen.
10-second answer, unfortunately.
Yeah,
okay.
The short answer is no, but it's more complex and interesting than that.
I knew that it would be complex. Okay. Any short one,
yes,
actually, from the room?
We have
Okay, we have one. Okay, please.
Hi, thank you for the great talk. I've got a question regarding your checking UBs. You've named like 80 UBs, and I'm wondering how many of those UBs can be now discovered by UB sanitizers or proper compilation flags, like almost all of them, half of them, or even less. Do you know that?
I would say most of them can be detected by sanitizers. There's a few limitations, like you cannot detect all race conditions. You cannot detect all uninitialized values. I think there's a few cases like this. But I think with most of them can be detected runtime. It's more like a question of, do you want to pay the cost for that, right? Do you want to pay 3x slowdown or 4x larger binary size in order to do that? So that's a decision you need to make. And I think Gaspar will talk a little bit about later about a new approach which kind of does these checks maybe more locally and than sanitizers do today in a way that's probably going to be not quite as expensive, but that's very much kind of future technology that doesn't exist yet. So I would say most of them you can detect, but it's a trade-off. It's not something typically you want to do always in production unconditionally because of the high cost.
Okay, thank you.
Thank you. Let's park it here. But as I understand, we are the community of people exchanging ideas. So even if we go for a dinner or for lunch, however you name it, there's still time to meet in the corridors. This is not devoted only for lecturers, but also for people who would like to exchange ideas. So this is Code Dive 2025. Now, the main hero for the next hour is just spending some time together over a plate of a good dish, which I really wish you for. There are plenty of options all around, also including in this building in the New Horizons cinema. So feel free to grab something to eat and come back to us ready for more, because there will be at least 3 or even 4 lectures ahead of us. Thank you so much for your time. Once again, huge applause for our speaker. Thank you, Timur.
Thanks.
Big thanks.
Thank you for having me.